51, na Rua Pamplona, São Paulo. Criado em 2017 como Centro de Produção e Difusão do Conhecimento e de Conexão da Ciência com a Sociedade, o Instituto Princípia tem 3 programas de atuação: um Centro Internacional de Pesquisa, a Escola de Talentos e o Domo Digital, onde se inserem atividades com o público externo. A Escola de Talentos oferece oportunidades de desenvolvimento pessoal e acadêmico a jovens que tenham grande interesse e altas habilidades para a ciência. O U-Science é um programa de orientação vocacional e de divulgação científica, voltado principalmente aos jovens que estão descobrindo as possibilidades da carreira em pesquisa. O cinema científico leva os espectadores a refletir sobre as questões presentes nos filmes por meio de uma discussão clara e objetiva. O Instituto Princípia também fomenta outras atividades de difusão do conhecimento, como artigos, blogs e podcasts. Conheça, participe, amplie seus horizontes através da ciência. www.institutoprincipia.org.
Okay, thank you all. Thank you all for all the participants to come to this workshop. I am glad that you all are here. Some are missing, but they will arrive soon. It's a pleasure to have you all here. This is a workshop funded by PAPESP and with the help also of ICTP, UNESCO, and IFT UNESCO. I want to start making a homage to the former professor Mahir Hussein. Mahir Hussein, he passed away in 2019. He was an Iraqi-Brazilian physicist. He left behind a distinguished career of achievements in broad range of physics disciplines. Here is in the early years in the Institute of Physics at the University of São Paulo in 71. Here is a short biography of him. In 1965, he got his bachelor degree in Baghdad University. In 71, his PhD in MIT. In 72, he joined as a physics professor at the University of São Paulo, and he was visiting professor of several institutions in US, Europe, in Japan. Recently, he was coordinator of Nuclear Astrophysics Group, Institute of Advanced Studies in University of São Paulo. He was affiliated professor at Michigan State University. His honors Guggenheim Fellow in 87, 88. In 95, Smithsonian Foundation Fellow at MIT, working with Feshbach, that you know, Kerman, Moniz, and Iacello from Yale Foundation's Nuclear Theory. 95, Scientific Secretary of Department of Energy National Science Foundation, Nuclear Science Long Range Plan. Gutzwiller Fellow in 2007, 2008 in Max Planck. He was member of Brazilian Academy of Science since 2000, TWS World Academy of Science 2005, Fellow of American Physical Society. Here, he was organizer of many events. I highlighted in green, I highlighted this one with Bertolani, Hussein, collective excitation and Fermi and Bose systems, where I was present as a postdoc at that time. I was a postdoc, and I was not registered previously, but I wrote him and said, "Oh, come, I will find a place for you." So it was the first time I met Bill Phillips, thanks to Professor Hussein. And there are other organizations, also several organizations on nuclear theory. He published textbooks in radioactive beings, molecules, atoms, and nuclei, and others. He has more than 340 publications, among them 71 letters in PhysRev letters together with PhysLetters B, 10 physics reports, And his main interests was mainly nuclear theory, laser-driven accelerators, random matrices, quantum chaos, and particular for us, Bose-Einstein condensates, symmetry breaking, and fundamental interactions, atom-atom collisions, and nuclear astrophysics. He was key leading person in a project to install superconducting solenoid system for production of radioactive ion beams at the University of São Paulo, later called RIBRAS, radioactive ion beams in Brazil. It has several very well cited publications I highlighted in green that are most interested for us. The first one is Feshbach resonance in atomic Bose-Einstein condensates, and that you know very well. This is for physics reports, where Hussein, together with Kerman, Tomazin, and Tiermans. And the other one, the other in green, is rarefied liquid properties of hybrid atomic molecular Bose-Einstein condensates. Also, his rev letter. So he has publications, several publications in nuclear physics, very well known, but he also has well-known publications in quantum gases in Bose-Einstein condensates. This workshop is part of a series of workshops organized by Mahir Hussein as part of a project or several projects in FAPEST funding. There was several workshops he did in the Institute of Physics in USP and also in Institute of Advanced Studies in USP. USP is like 12 kilometers from here. Fortunately, this place is much more convenient to be here. And I highlighted in green what was more relevant for us. Is the workshop, the third one, is the workshop on Bose-Einstein condensation and quantum chaos. It was in 2015. It was in Advanced Studies in USP São Paulo. And the last one, also in green, is the Institute of Advanced Studies International Workshop, Physics of Cold Atom Gases, Order and Chaotic Aspects, in 2019. Some of us were there, including mine, of course. I was in this workshop. And so our meeting on Bose-Einstein condensates or quantum gases was already envisioned by Hussein to be somewhere in 2021 or 2022 by his prospects. And it's an honor to continue his efforts in promoting science in different fields. I'm sure he hoped you have an enthusiastic workshop. First of all, I want to thank Hussein for his efforts in science for us. It was an effort that he did many times, so we somehow owe to him for envisioning this workshop for us. I want also to thank Professor Axel Pester from Kaiserslautern University for accepting to be one of the organizers. He helped quite a lot and was really shared the organization. I also want to thank Nathan Berkowitz, director of the Institute of ICTP Site-FIR, Jandira Oliveira, executive manager that you met just now, and Humberto Neto, executive secretary, and also the staff of IIT Foundation, Gerson Francisco, and Norma Regiani, events manager, and Wellington Barbosa, audiovisual, and also now today I met Luis and Milena that are projecting this for us. So now we start with the program properly. So the first section is about manifolds. We will start with Nathan Lundblad. I will call him. I just want to tell you that the dinner is tomorrow. There was a misprint in the first booklet. The dinner is tomorrow, okay? So thank you all and have a very nice workshop. I hope you enjoy everything.
Oh, wonderful. I have to say, this is one of the most amazing spaces I have given a presentation in. It's really quite wonderful here. I have a little bit of feedback on my microphone. Should I adjust it or should I keep speaking? I think I'm okay. Oh, wonderful. Thank you, Arnaldo, for a wonderful introduction. It is a great pleasure to be here. I have never been to Brazil. I have heard many, many wonderful stories when I was a postdoc from Bill Phillips about physics in Brazil, in particular about São Carlos. And I'm excited to be here finally. It's a very easy flight for me, and particularly with no jet lag, which is particularly wonderful for international travel. So today I wanted to tell everyone about some experiments. My feedback. A little bit. Is that a little bit better? Good? Okay. I feel a bit like a rock star, dealing with feedback from the large speaker banks like I'm Freddie Mercury or something. It's a nice feeling. I am not Freddie Mercury. So what I'm going to talk to you today is about these experiments on ultracold bubbles in space. And in the spirit of the workshop, I put a little highlight in yellow that this is an attempt at a low-dimensional quantum gas on a curved manifold. I think I'll put a note later that we make no claim about the two-dimensional nature of these. We think we're getting fairly close. But the spirit of these experiments really is to place a quantum gas on a curved manifold. And I'm from Bates College in Maine, and I'll show you a map in a second. And these are all experiments done in collaboration with the Jet Propulsion Laboratory and with the US NASA organization. All right, so you can see in the upper right there, the US state of Maine. So Maine is the far up northeast of Maine. In the entire state, there are 1 million people. So just by comparison, I think that's maybe the 3 or 4 blocks right around here. So it's always nice to come to a genuine metropolis and have a different feeling for me. Because even if I go down to a city like Boston, which is closest to me, it's nowhere near this size. So it's really fantastic to have this experience. The state where I'm coming from, Maine, is most famous in the USA for this animal. Does anybody know what that animal is? It's a lobster. People come and they go on vacation in my state, and they come on vacation and they eat lobsters and they go home and then they tell everybody about it, or they pay a lot of money in their own state to have lobsters sent to them. I don't like lobster very much. It's not my favorite, but it does bring a lot of economy to my state, which I appreciate. So I'm a friend of the lobster in that regard. There's some theoretical collaborators we've been working with. Smitha Vishveshwara's group at the University of Illinois, which is in the middle of the US there, and all my collaborators at the Jet Propulsion Laboratory are in California. So maybe a very sort of biggest picture of what I want to talk about today is to try to think of different homes for quantum systems. And in this case, these are very literally different homes. Can we do experiments focusing on quantum dynamics that are not in our laboratories, in the basements of physics buildings? Can we actually go to places like the International Space Station or in orbit or in space probes and access the same kind of physics and use the advantages of such places to do that? So a quick outline of my talk today. I want to sort of motivate what we're doing, and then explore and explain this experiment NASA CAL stands for Cold Atom Laboratory aboard the space station, and summarize the recent experiments we've been able to do to make bubble-like structures with ultra-cold atoms, and talk about what the best parts are of these experiments and maybe some of the non-ideal parts as well, and summarize what we would call the run 1 and run 2 observations, And there's actually an upgrade to this machine that's being launched fairly soon, and I want to talk about some dreams we have for the upgraded machine as well. In the spirit of this session, I wanted to highlight the fact that there's been many, many recent theoretical explorations in this area, and some experimental as well. I'll focus on the experiments a little bit later. But in particular, there's been folks here in Brazil pushing hard on this area to understand the physics of bubble-trapped condensates and quantum gases and curved manifolds. And I've always had a version of this slide, but it's now getting too busy where you can't read, you're starting to not read the individual titles, which is good news, but it means that it's just going to get illegible after a while. And in particular, in this session, we have talks by Santos and, forgive my pronunciation, Caracas. Okay. All right, so in the spirit of our current era, last night I was bored and I started interacting with the artificial intelligence program ChatGPT. Have folks heard of this a little bit in the news? So it's actually quite remarkable. So this is ChatGPT 4, the latest version they've released. And I've asked it some questions. So can you tell me some neat consequences of ultracold atoms being on curved manifolds? And it's not wrong. It's actually kind of a nice summary. And the English is nice. It's the sort of thing that I might put in the beginning of a grant proposal. It's quite shocking. Perhaps more shocking, I picked one of those theory papers, and there was an operator that I was like, oh, I don't remember what that looks like, or I wonder if ChatGPT knows about it. So I said, hey, can you give me a specific form of the Laplace-Beltrami operator on a curved manifold? And it not only gives me this, it gives me the LaTeX that I could then copy the LaTeX, and it's correct. So the reason it knows about this is because it was trained in maybe late 2021. So anything in the physics literature that is on the internet that is sort of reasonably cited or public is part of the training of this neural network. So like if I ask it about something that only occurs in a physics paper in 2022, it's probably going to be, it's going to not be right or be confused or give strange results. But it appears to be very well trained as a language model on all physics texts that are easily accessible on the internet in 2021. So I found this I expected this to be kind of a joke, like, haha, it's close, but not quite right. But this was actually pretty good. I think it means that we all have to evaluate how we think about how we interact with these programs. And I asked, it also gave me a little qualifier there. So it's trying to be shy. That's a shy artificial intelligence. Like, oh, don't you shouldn't believe everything I say. But it's important. It's really a neural network that's optimized on finding the next letter of a statement. So, but on the other hand, the utility of this seems pretty fantastic. All right, so that was a side road, but I spent enough time thinking about this last night that I wanted to share it. Okay, so we want to enter a time machine and go back 20 years and enter this idea starting to talk about the properties of coherent matter wave bubbles. And this was an idea that Barry Garraway, who I know some of you have met, came up with and first published around then and explored, well, given the recent at the time, production of Bose-Einstein condensates, maybe we could make them into bubble geometry or shell shapes. And he started looking at how you might do that. Another way to think of it is that we're trying to come up with some potential U of R that for a given temperature and density of atoms will result in a bubble density distribution. Unfortunately, given the practicalities of doing this, this is very difficult to do in the presence of gravity. There are some tricks to get around that, but they're very difficult. And I'll summarize some of those tricks a little bit later. So many people have been acquainted with the idea of levitating atoms with magnetic fields. So we could think of, for example, levitating the atoms with DC magnetic fields. And this has been done. You can probably even Google pictures of someone levitating a frog with magnetic fields. The trouble is the trick that we use to make bubble clouds or ultracold bubbles involves what's called radio frequency dressing. It's a superposition of spin states. And if you have a superposition of spin states, they have different magnetic moments. And so the levitation trick for DC magnetic fields won't work. You can imagine saying, let's use a gradient of Stark shift. So for example, a laser with spatially dependent intensity, like the side of a Gaussian beam. You could do this, and a group in Tokyo has actually tried to do this with some success, but it's very difficult to get it to be uniform and precise to a few percent over large sizes. And certainly for the sizes of bubbles we want to make, we don't know how to do this. But in principle, it's possible with a high enough power laser and precise intensity control. A new idea that's floating out there is to actually what I would phrase as AC magnetic gradients. So having a gradient of the coupling strength of a radio field. And Helene Perrin's group in Paris has met some success doing this, but making that gradient uniform has proven to be very difficult. Okay, so maybe we can cancel gravity and try to make these bubbles that don't sag to the bottom of a shell using other means. And maybe one way to do it is to make the atoms repel each other and use very strong interactions to do this. We can try to do this, but it turns out for the atoms we're using, typically rubidium, maybe potassium, we don't have the condensate numbers to do this. Maybe if you have condensates of billions of atoms at the right size, you might be able to do it, but this is one of the things that has prevented this on Earth. Wolf von Klitzing in Greece, or actually at Crete, has come up with some ideas to shake a trap and through some kind of modulation, cancel out gravity at least partially. But we haven't figured out how to do that uniformly or strongly. All right, there is another way though, and this is actually a pretty fantastic idea that I'll devote one slide to. And it's actually not worry about gravity, but make two clouds of two different species and have one species be a core and a second species be a shell. It's almost like a fruit with the skin of the fruit. And this relies on a differential scattering length between them. They actually, to lowest energy, prefer to be phase separated. And we have, for example, in this case, a potassium shell surrounding a rubidium shell. And this is a clever idea that the folks in Hanover and elsewhere came up with a couple years ago and has actually been executed by this group in Hong Kong. So on one hand, that's great. It makes a lovely shell. It's difficult to tune the size of the shell because it's relying on interactions and the number of atoms, and it's difficult to dynamically alter. But I would be sort of remiss if I didn't mention that this existed. And what this means is that there's now sort of two competing experimental techniques for making bubble-shaped ultracold gases, which actually I think is only a good thing for the field. All right, if you want to cancel gravity, you could even do something a little more scary. All right, you could throw your condensate machine up in the air and have it go into free fall. And a few folks have done this. The folks in Germany have been putting BEC machines in a drop tower where they lift up the BEC machine and it drops. And while it's dropping, you make a condensate and you take a picture, and you do your physics. And then you lift it back up and you drop it again. In that case, you're limited by the time of flight of the dropping. And you're also limited by the fact that you can't do it so often during the day. Although there's a new apparatus in Hanover that should improve upon that. You could put it in an airplane and send an airplane in ballistic flight, take your BEC machine and throw it in an airplane and get maybe a few minutes of free fall, of zero gravity. That's been done. And there's ways to do this in the lab where you sort of repeatedly lift up, drop, but on maybe 1 meter or 2 meter scales. You could launch it in a rocket and have a rocket launch go up in the air and go above the atmosphere, come back and do this. So the Mayas machine has been launched once, and I think they plan to do it again. And this gets a few, more data than just dropping it in a drop tower, but not as much as you would get maybe in launching an airplane, although it's close. They get maybe 10 iterations or 20 iterations or 30, I believe. All right, so the final way you could do this is actually say, free fall is good. Let's put our BEC machine in free fall, but let's have it be in perpetual free fall, ongoing free fall. And the way to do this is to go put it into orbit. I don't know how to do this because I have a laboratory in a basement of a science building, but we can ask the people at NASA and JPL because they decided to build one. That's the International Space Station on the right. Inside there, there is an astronaut hanging out. Note that he's not in a spacesuit, so this is not. This is at warm atmospheric pressure. The only thing different from Earth is that we're in free fall. So the fact that there's a cold atom machine on the space station has nothing to do with the fact that space is cold or space is a vacuum. It's just a way of having the apparatus be in free fall. Now, you might think that having this apparatus should be well isolated from the astronauts, but you can see that little blue sticker right there that says Cold Atom Lab, Cold Atom. That's right there, in the middle there. I realized I'm not using the zoom pointer. Is that okay? I think it's okay. So does anybody here know what this astronaut is doing in this picture? Any guesses? He's getting some exercise. He's riding his bicycle. So this machine that I'm going to tell you about is placed right in their gym, their gymnasium. And for some of the experiments that people do, I think there's a few worries about vibration, having someone riding a bicycle right next to it, but it hasn't affected a lot of the research. I think that's because the experiment is fairly well built and isolated and sturdy. So all of this spaceborne cold atom machine is in a rack of equipment, roughly about the size of a medium refrigerator on the space station. And it's operated remotely from the ground from California and not by the astronauts. The astronauts installed it. The astronauts plugged in the fibers and the cables, but they do not operate it. It's operated remotely. So maybe a few facts about the NASA Cold Atom Laboratory. So the NASA ISS has been in low Earth orbit for about 15 years. It's equipped with a bunch of equipment rack slots for people to put scientific experiments in. A lot of the experiments they have done have involved the growth of biological samples in free fall or the study of combustion in free fall. Honestly, not a lot of fundamental physics has been on the space station until now. Some, but not a lot. In particular, what does the Cal facility offer us? So as physicists on the Earth, and if NASA comes to us and says, hey, we have a machine in free fall, what can they give us? Well, one nice thing is that all cold atom experimenters sometimes want to make very weak traps. So they're holding a trap together in a bowl and they relax it and they go weaker and weaker and weaker. If you do this on Earth, typically this means that the trap sags and eventually gravity overwhelms the trapping forces. And if you're in free fall, you don't have to deal with that. So they can expand their condensates to be very, very weakly trapped. You can have very long time of flight expansion. Typically in a laboratory on Earth, to study a condensate, I drop it and let it fall. And as it falls, it gets bigger, and I understand its momentum distribution that way. On the space station, I can get very long time of flight, because when I release it, it just stays put. It's actually quite remarkable to see. It just sits there in the middle of the vacuum chamber. Maybe a little bit more technical or a little more specific to my desires. We eliminate gravitational tilt. So in particular, I use rubidium. So what is gravitational tilt for rubidium? In thermal units, it's about 100 nanokelvin per micrometer. And if you do experiments or you collaborate with experimentalists in this area, that's actually quite a strong gradient to have 1 micron result in 100 nanokelvin of thermal energy. And it actually means that we really can't do these experiments on Earth. But if you eliminate that, or even eliminate most of it, you can get a lot of possibilities. And maybe the last point I would make about what this facility offers us, it's actually a different social aspect of doing science. Typically, as cold atom scientists, we don't go to a user facility. We don't go to like a particle accelerator or a high magnetic field facility or an X-ray beam. We do our experiments in a lab where we work. And this is different. This is a user facility that is elsewhere that we apply for time on the way other physicists do. So it's a bit of a different social aspect to doing physics that I've found interesting. There's a few papers out there describing the sort of technical details of how this apparatus works, including sort of blowing up what's inside those rack mount capabilities. This is a so-called atom chip machine. It's a very compact BEC apparatus with the planar electromagnets of the atom chip governing most of the physics. NASA has been talking about doing a condensate in space for probably 20 years, but it's only in the recent years has this become a method that was cheap enough or inexpensive enough to be able to fit it into a small space and be able to do practically. So this is a sort of classic making BEC picture from the folks at Jet Propulsion Laboratory at NASA. So this is not my work, this is from the group that runs the machine. But this is where in this paper, they actually showed that this machine works. It makes a BEC on the space station. And you can see the sort of classic thermal cloud through condensate. Because it is an atom chip machine, it makes very, very high aspect ratio condensates. So you can see some of the asymmetric or anisotropic expansion on the right there. They can do free expansion times of about a second, which you can imagine if I drop something, how far it would fall on Earth in a second. We can't do that in our labs on Earth. We could do it with a fountain by tossing things up, but in a typical laboratory, we can't. The machine has capacity for radio frequency application, microwave application. For potassium, there's a Feshbach resonance. Unfortunately, rubidium's Feshbach resonances are like at 1,000 Gauss, so that's a little too high. But for the potassium, it's pretty useful. And there's also Bragg interferometry beams for doing atom interferometry. And I think one of the key goals of this apparatus was to explore studying atom interferometry of potassium versus rubidium and look toward an Einstein equivalence principle test. A couple of neat notes about this apparatus that I found counterintuitive is that evaporation works differently. So evaporative cooling typically works by reducing the strength of your trap and letting the hot atoms fly away. And on Earth, they fly away downwards because gravity is preferentially pulling them. In zero gravity, the atoms that are evaporated fly away up, down, left, right, everywhere. So it means that optimizing how evaporative cooling works becomes a little bit of a different path. The atom chip, because we chose to make a small apparatus, the atom chip is a small apparatus, it means the condensate size is a little bit smaller than some people are used to. So a typical condensate in a typical laboratory on Earth might be 100,000 atoms, or sometimes even more than that, but atom chip machines typically are limited to tens of thousands of atoms, maybe 10,000 atom condensates in this spirit. And I say helium in capital letters there, because the space station actually has quite a large partial pressure of helium, because there have been experiments that use helium for cryogenic experiments, and they dump the helium and it builds up in the space. So it's not enough to be unhealthy, but it means that there's probably, I don't know, 100 times more helium on the space station than in this room. And it actually affects the vapor cells that they use to lock the lasers. So that's maybe a special fact for the people who work with laser absorption spectroscopy. Maybe one other interesting fact, these absorption images of cold atoms on the space station, this is after a gradient has been applied. So there's been a Stern-Gerlach gradient applied. And so we can see different spin components, including a zero magnetic moment component there that on Earth would have just fallen away. It wouldn't have been trapped in, it would have fallen away, and we have never seen it. But now, as we evaporatively cool, there's a little bit of that left, and it hangs out, it stays around and doesn't go away. And sometimes this is good, sometimes this is bad. All right, so the PAL machine has several users right now. So the idea is that NASA built this machine and they put out a call for proposals 5 or 6 years ago to say who has an idea to do physics on this machine. And these are the proposals that are working on the machine right now. The one I'm talking to you about today is here. And some others that you can browse through. All right, so I want to talk specifically about these shells now. So I could go back to ChatGPT and say, can I make ultracold bubble structures on the ISS? And remarkably, it describes making a condensate. And then crucially, it says it could involve shaping the trapping potential using carefully designed magnetic or optical fields or employing radio frequency or microwave dressing. Thank you, ChatGPT. That is what we will do. So the old trick that we are using to make this is to look at radio frequency coupling of spin-dependent potentials. So if we have multiple spin states and we have an anisotropic magnetic field that is trapping the atoms, we can couple them with radio frequency and create so-called adiabatic or dressed potentials. You could think of them as effective potentials too. The details of this are laid out in a paper at the bottom there, but that really is recapping some of just the modeling efforts we went through over the years. This idea of doing a shell via radio frequency dressing actually dates back to Barry Garraway in the early 2000s. All right, so the real potentials are a little bit more complicated, but let's look at a simplified case first, with just 2 levels. So if I have a trapping potential for one spin state and an anti-trapping potential for another spin state, and I couple them with radio frequency, at that point in space where the radio frequency is resonant, I'm going to form a notch in this adiabatic potential or this dressed potential. So you should think of this as maybe another way of thinking about it is I have moved from the lab basis for spins to a dressed basis for spins. And in that dressed basis, these potential curves become these potential curves. So the upper one is one I'm most interested in here. So to our eye in this picture, this looks like a double well. We've used radio frequency to split this potential into a double well. If you take that idea and you rotate that into 3 dimensions and to think of this as a radial coordinate, it's like we are repelling atoms from the middle of the trap. And if you repel atoms from the middle of the trap, that is how you would form a bubble. It doesn't say anything about how thick the bubble is, whether it is a thick-shelled bubble or a thin-shelled bubble, but the basic idea is this. What's nice about the calculations of doing this is that it's, actually I have a lot of very capable undergraduates in my institution, and I can give them the modeling for this once they've had a little bit of quantum mechanics, because it really is just sort of Zeeman shifts and rotating wave approximation and a few other things, and they can make productive modeling efforts pretty fast as undergraduates, which is nice. So as with all experiments, the real potentials are a little bit more complicated. We use an atom chip, which has a very strong cubic anisotropy. So you can see that the potential trap is locally harmonic. It looks like a usual well if you're very local, but it has a very steep gain toward the atom chip on the left and a slow roll off to the right. And so when we dress these with radio frequency and make these effective potentials, they have a little bit of a tilt, and they have a little bit of a differential squeeze between them. So looking at that tilt there, you see how the yellow curve is not on this, does not have the same floor. You might say, didn't you just say we're in free fall? Why are, didn't we get rid of gravity? This is where one of the first non-idealities of these experiments comes into play. So these dress potentials are essentially avoided crossings. So it's a classic Landau-Zener coupling with an avoided crossing. And those are the avoided crossings in there. The coupling strength is different at that point in space versus that point in space. And this is because my radio frequency comes from an antenna over here. And if my radio frequency comes from an antenna over here on my left, the strength of the radio frequency here is strong. The strength of the radio frequency here is weak. And if the coupling changes with space, the gap in the avoided crossing changes with space. And that results in a little bit of a tilt. It's small, it's not large, but it's enough to affect some of the data we see. We can change the dressing frequencies and the power of the coupling to change the radius of this shell. And these are slices through the shell. And we can change the tightness of it. So in the spirit of moving to a two-dimensional gas on a curved manifold, we might imagine tightening up, going from a loose bubble to a tight bubble on the right. And these are dynamic changes that we can make during an experiment. So why microgravity? I've said that this was caused irretrievable sag. People have tried this on the ground several times, sort of most notably in Helene Perrin's group. You can see a condensate viewed via absorption imaging. They are trying to make a bubble here, but because of gravity, it sags to the bottom of the shell potential. This actually is advantageous for them because it makes a nice tight 2D, almost contact lens or bowl-shaped trap that they could use to study some 2D physics. But because of gravity, it doesn't fill the whole shell. Brian DeMarco's group at Illinois also saw this, and we see some data here from Chris Foote's group at Oxford, where they're seeing the same thing. They're doing some neat tricks here with nested shells, which is a possibility to do as well. But again, gravity pulls them all to the bottom. All right, so how do we actually do these experiments on the space station? So the first thing we do is we ask the user facility for a BEC. So, hi NASA, please give us a BEC. I try not to involve myself in those details because I'm a user of the facility. But I know that they make a BEC using typical atom chip techniques. The one they make is actually a very high aspect ratio, maybe 5:1. So it's like a pencil or a stick. That's not really useful for us for making these bubbles. We want to start with a condensate that is maybe more spherical. So the first thing we do in these experiments is move the condensate away from the chip and expand it and change its aspect ratio. This is necessary just to get the aspect ratio, but anytime you move a condensate and yank the potential from here to here, you have to be very, very careful because you'll start shaking it. It's like carrying a bowl of jelly. It's going to start moving it all over the place. So as we do this, if we make that motion very violent, if we take a small condensate here and we pull it away from the chip, we start oscillations. And you can see these oscillations at a particular amplitude there, maybe 100 microns or so. So that's bad. That means that if the experiment you want to do involves a condensate that's rolling around, it's not in the same place. That's terrible. So we need to be more careful. So we can carefully move it a little slower, and the oscillations get a little bit more damped, or the little bit lower amplitude. And eventually, if we are very careful and we just do this very slowly, we're limited mostly by some residual noise in the trap. And if we plot that amplitude, so that data point corresponds to the upper left there. If we are more careful and we more slowly expand or pull the condensate from one side to another, it will be still and it will be at rest when we start our bubble experiments. So before I show you some of the data that we see, it would be useful to understand what we might expect. So we have a model of what this would look like based on the magnetic trapping potential of the atom chip and what the bubble should look like. As anybody who does cold atom experiments might understand, One of the difficulties that we have is the way we take a picture is by sending in a laser to take a shadow image. We do probe absorption. And that means that your data is actually going to be integrated along the direction of the probe. So if we send in, even if we have a pure looking bubble, we're taking a picture of its shadow. So what that means is that any anisotropy of the bubble is going to be a little bit exaggerated. On top of that, we don't actually have a specific, infinite resolution picture of this. We're blurred by the resolution of our imaging system. So we can make a model of this trap and see what we expect to see and apply a blurring associated with the resolution of the apparatus. So if I don't blur it very much at all, if I don't account for resolution, I might see a hot bubble gas that I expect to look like something like this. And if it's a little colder, it will look something like this. So the fact that they are preferentially toward the bottom of your screen is coming from this anisotropy in the coupling strength. So these models that we are looking at here are of column density. So they are integrated along the distance of line of sight, as illustrated here. So we're looking from the right, the probe beam is coming from the left, and so forth. The second thing I want you to be aware of is that even though this looks a little bit, I think to my eye, not like a bubble, it's very clearly sagged, it's been integrated along the line of sight. So what I can do in our model is take a slice through the density distribution. And even though I won't have data that looks like that, I can at least see what the slices look like. So this green dot, the green dashed line there corresponds to this green box here. So we just would see a blob there. That's because that slice only sees a blob. If I take a slice through the middle, the density distribution will look something like that. And that sort of reassuringly looks a little bit more like what you would expect from a bubble. And as I go back, I again see something like this. But when I add these 8 images together, they form the image at the upper left, which is a little bit less bubble looking. Okay, so when we actually do this, what do we see? So if we start with a hotter gas, we see something on the left that looks like this. The condensate initially started in the middle where that black dot is, and the black bar at lower left represents 100 microns. If we start with a colder gas, which by necessity means we have fewer atoms, and so the signal to noise is worse, we see something similar, but with some interesting features beginning to emerge. So when you look at this, I think what you first see is cooling to the left and to the right. So there's clearly some anisotropy in the density distribution to one side or the other. There's also a strong preference to be on this side, on the bottom in this picture versus the top. If we had the capacity to experimentally take slices, like tomography through these images, I would expect that we would see things more like this. But when we add them all together, they form clearly biased looking images like this. So how can we interpret this? When I first saw this, I didn't really know how to interpret. So we really had to go to that model to sort of look what happens when we do column density integrated, blurred by resolution images of these bubbles. It's worth noting too that if this scale is 100 microns, if we were on Earth, at the rough temperature that we know of these, this key scale, KT over mg, is a few microns or a few micrometers. So if we were on Earth, this would be pinned to the bottom few pixels in this screen. So regardless of the shape of it, which I think we have to do some interpretation on, if we did this on Earth, it would be almost a flat line, just sitting at the bottom couple of pixels of this screen. So a few ideas to kind of summarize how we do the modeling here. We really need to start with what the atom chip does and what its Biot-Savart magnetic field is from the known currents. And as we go from there, we can calculate what the trap potential is, apply this dressing formalism, and come up with a dressed potential. And what can we do from there? We can solve GPE in that potential. We can find a thermal density distribution in there. And we can actually make some predictions of what the density distribution should actually look like. And depending on how the blurring works, how this imaging resolution works, we see a couple things that are of interest. So starting with maybe at the lower right here, if I had a model that didn't include imaging resolution, I almost wouldn't see the left and right features there. But when I apply imaging resolution, you see the features at left and right start to show up. My student thinks this looks like the eye of a gecko, which I don't know if a gecko or newt, some sort of animal. So you should see two little eyes there looking at you. As we've expanded into this bubble, we've started maybe with an initial temperature of 90 Kelvin, going to 20 nanokelvin in the model, but in reality, it's not quite so cold. So in the spirit of this talk, and to forestall a question, I don't know if this is 2D yet. If we are adiabatic in this shell, given the initial temperatures, I think we would be, but I'll show you some thermometry and temperatures in a second. That means we're not really sure that we're in the 2D, but we're close to it. We can go to much, much larger shells. There's no good reason to do this because the anisotropy, or the pull to one side, becomes extremely powerful when you get to millimeter-sized shells. But I think it's worth doing just to show what it looks like. So you should note the length scale on the left of about 1 millimeter. Each frame of this movie was a separate iteration of the data set because the imaging is destructive. And if we really push it, we can get these sort of hemisphere, they're not, I don't think of them as bubbles at this point. We can get these strange hemisphere structures that are at multiple millimeter scales. The feature that you see remaining in the middle there, we're pretty sure is not at the core of this ellipsoid. It's actually on the sides. It's just in column density. You're seeing it in the center. And maybe you can note on the right, that's the surface of the atom chip on the right there in these structures. All right, so those pictures that I showed you were all from the first run of this machine. The apparatus was upgraded a couple years ago to have stronger RF, to have more uniform radio frequency, to improve the tilt, and to actually improve the aspect ratio. So we haven't fully analyzed all of these, but the basic idea is that the shells look better in the new hardware. And on top of that, we have a second imaging axis. So we're not just imaging from one side, we can do imaging from a second axis and actually sort of have a better confirmation that we understand what's going on. So along the same axis as before, we see structures that look like this, zoomed in, zoomed out. And if we look from the other direction, maybe looking from the top of these pictures at the left, we also see similar structures with this pooling to one side. And the pooling is coming from a couple different factors, but mostly the anisotropy or ellipsoidal nature of this shell. Importantly, this is, we don't know if this is a condensate. We start off with a condensate, and we will do some thermometry, which I'll finish up showing you some thermometry. But there's not a smoking, or there's not clear evidence right now of a BEC in a shell, and I want to be careful about that. All right, so how do I think of the thermometry? Actually, let's skip a few slides here. There we go. So inflating this bubble, and as we go from the harmonic trap, dynamically increase to a bubble potential, it is equivalent to an adiabatic expansion. The temperature should drop at constant entropy, approximately. So we can do this by starting with a hot gas. So I'll walk you through these graphs starting from the left. So the horizontal axis is an inflation parameter. It's essentially the radius of the bubble. So we're starting from no bubble at the left of the x-axis and going to a bigger bubble. So two things happen. The temperature does drop, and you can see we have a model in shaded there predicting what it should drop. Critical temperature, TC, also drops, which is as you would expect with an adiabatic expansion. But we're still, in this case, very, very far away from a condensate. This is a deliberately hot gas at left. So if we start off colder and see what happens, things still work. And as we start off a little bit colder, the thermometry is starting to indicate that we're not getting as cold as we should get. And if we start with a condensate, so the red dot there at far right, if we start with a condensate and then we increase the bubble size and take the temperature of the bubble, it's not as cold as we think it should be. And I put that green line at right to represent the temperature at which I would think we are sort of in a genuinely 2D regime. So we're close, but not quite there. So the question is, what's going on here? When we do this thermometry, we're starting off with a bubble structure that looks something like this. That's already maybe 1/10 of a millimeter, and letting it get bigger and bigger and bigger. And then we're measuring its width in time of flight to get temperature. This is a usual technique, but it's a usual technique for very small clouds. With this big cloud, it's large compared with the depth of field of the imaging system. So there's the imaging could be messing with this. The thermometry algorithm we're using could not be particularly good for large clouds. But it's also possible that we are not adiabatic. That is, we started with a trapped condensate, and we inflated it into a bubble, that we did that too violently, that we added entropy in that process. So a lot of what we're working on right now with the machine is trying to understand the adiabaticity of this process, maybe by inflating a shell, then deflating it, and seeing how hot it gets afterwards. It's likely that both of these are going on, that we're probably both non-adiabatic, and there's something fishy with the imaging or the thermometry. So we're trying to figure all of that out right now. But what it means is that when we do time of flight, we don't see, for example, a clear, sharp feature in momentum space that is sort of lets you know that a condensate is there. But it's possible that it's there and the imaging is bad, but it's possible that we heated it up as well. It's sort of it's an open mystery now that we're spending most of our time working on. And maybe what I'd like to finish with is just something fun we did to see what it looked like, because this was a bit of a playground when we were doing it. So if we start off with a ultracold gas in a bubble configuration, and if I look through it in 1D, it looks like this. There's some density on one side, some density on the other side. If I turn off this dressing and let this gas evolve, kind of like a quench, not quite, but it's a quench to a harmonic trap, we should see some fun stuff. So depending on how large it is, we can make a movie of this, and there's unfortunately 5 frames of this movie. So if we start with the usual shell that I showed you in the last one, we see different frames of the movie that look something like this, really strange structures that come out of it. One thing I was hoping to see with this is that we would start with a bubble that would collapse inward and sort of interact strongly with itself at the center of the bubble, and see some kind of loss like a Bose-Nova effect from long ago. We do see some spikes in density in the middle sometimes, and it's roughly at the frequency you would predict from the trap frequency. But mostly these are just curiosities. You can start off with bigger ones and really see some strange density effects. This is starting with a thermal gas in principle. This is all calculable with some sort of Fokker-Planck thermal evolution in a dynamic potential, but it's yeah. You're saying that this is hot? So the blue trap, the critical temperature is maybe. So in this trap right here, I mean, the temperature, the case right here is this is wildly out of equilibrium, right?
Below the critical temperature of that trap.
If I did it in equilibrium, I would expect it to, but I think we are not being adiabatic. I think if we make the bubble and then we come back, it should still be a condensate. But I think the way we inflate it is shaky, and it's also possible that the main thing is that the inflation is shaky. The second problem is we're starting out at maybe 90% of TC. So it's not a very good condensate to start out. It's just barely a condensate. So even a little bit of extra energy causes trouble. Yeah. So the main idea that we have here and is that this radio frequency ramp that does this inflation that results in a change in radius at some level is not smooth. So the radius changes in steps, and we have to tell the hardware to make smaller and smaller steps. But getting them small enough is it's a engineering problem, and maybe the steps, whenever that step jumps in the radio frequency ramp, it's like the bubble radius goes, it hops, and so it's non-adiabatic. And all we can do is try to make that as fine as possible. So it's possible that that's a problem. The second thing that maybe is a little bit more physics oriented is, I don't have a good graph of it, but as you inflate to a bubble, there's a point where you go from a bowl in the middle to a hump. It's like going to a Mexican hat. And the point where you go from a bowl to a hump, there's a point where the bottom is quartic. And when you're quartic, there's no time scale, right? The time scale for adiabaticity becomes infinite, and we can't meet that criterion. So there's always going to be, I think, a little bit of a problem. It wouldn't be a big deal if we were starting off very, very, very cold, like maybe 0.1 TC, but we're starting off at maybe 0.8 or 0.9 TC. So even a little bit of heat causes problems, I think. And so that's one of the hopes for the next generation machine, is to start off at maybe 0.2 TC or 0.3 TC. In the spirit of that, I think actually I will finish up and show you a summary. There's a lot of text here, I apologize. But the future, and maybe I would focus here, what I would call run 3. There is an upgraded machine going up that is supposed to have lower TC or lower temperature, more BEC numbers, because the more atoms there are in the BEC, the better signal to noise we have, and just the better the data will be with more numbers. We also want to try this with microwaves and try this with multiple frequencies. Ultimately, there's a lot of physics goals associated with this project that would want to look at how vortices behave in curved manifolds. We can't generate them on this apparatus right now. The next generation apparatus has some shaking capabilities to take the bubble and rotate it in ways that should deliver angular momentum to the system to bubble it. What we don't have is a stirring rod. The classic method that we would really want is to send in a laser and stir the condensate and generate vortices that way. And we won't have that, but we should be able to do it by tilting and rotating the condensate a little bit. And there's also the possibility for doing Bragg spectroscopy. So actually trying to get the temperature through ways that are not this time of flight expansion. And in the longer run, maybe in the next sort of 3-4 years, the German NASA DLR, the DLR and NASA are collaborating to launch this machine BCAL, which should be an even more optimized machine. So there should be a second generation or third generation of this hardware, which is really exciting to see. So I think I'll just put up some pictures of people I've worked with and say thank you, and I'll stop there.
Thank you very much, Nathan. So questions, please.
Right there.
Yeah, thank you, Nathan. I had a question on your definition of TC. You were showing these plots when TC was dropping as you were increasing the bubbles, I think. Yeah, so is this TC in a three-dimensional system, or is it a...
No, it is TC modeled for that particular trap.
Oh, okay. Which is effectively still a three-dimensional system.
It's a three-dimensional system.
But very thin in one dimension.
Right. So I mean, it's the reason why it's getting flat, and depending, I like to think of it as that at that point it is almost two-dimensional, and so TC is not changing much anymore. Like locally, the atoms just see a tight squeeze in two dimensions. So the region of strongest change is where the density of states is most dynamic, where all the interesting stuff in this inflation is happening as I go from a bowl to a Mexican hat.
And do you have an estimate for what your effective trapping frequency in this tight direction is?
By the time we get up to there, it should be about 1 kilohertz.
Okay.
So maybe 50 nanokelvin or so. So you see 50 nanokelvin there. That's why I put the green right there. And it doesn't change much. It's probably, 800 hertz there and 1 kilohertz there. So that all the interesting dynamics of the inflation happen in the beginning. And that's where I worry about the non-adiabaticity the most. There's some interesting stuff about TC changing in ways that are not commensurate with temperature, because it's like these dimple traps where you get different aspect ratios, and phase space density does not necessarily track with entropy, but that's maybe a second order issue. Up there.
I have a question in the sense of motivations for studying this bubble and zero gravity. What do you want to do with this? Is, for example, I read in some papers that people in this area are looking for some new effects, new observations in quantum mechanics, for example. So the idea is go to a more fundamental way on quantum mechanics and understand things that we cannot see in other manifolds. But because I was thinking it's hard to do this here on Earth because of gravity. So is this the idea?
Yeah, I think to be quite honest, when we first did this, it was more motivated by curiosity of what a bubble BEC would look like. Like the history of BEC is people trying different dimensionalities, different topologies, different interaction strengths. But if we then say, okay, fine, that's very nice to be curious, but what's actually different on these topologies? And I think it comes down to the behavior of vortices. As you have vortices that are going to move in an effective potential that's given by the curvature. And I think seeing that and understanding how they behave is what I think I don't understand very well, and I'd like to answer. So maybe a second way to think of this is that if you want to do atom interferometry experiments, you need a very cold and very stable initial sample. And the inflation into a bubble state cools them and also but keeps them not dispersed over a large volume. So the signal to noise of this is still high. So it actually might help with some of the atom interferometry fundamental physics applications. But in terms of sort of understanding quantum mechanics better, it really comes from understanding what happens to these quantized excitations, vortices, and how do they behave in a curved space-time, if you like, and how can we understand that better? I think there's also significant interest in understanding the collective excitations of a condensate in this geometry, but I think of that as more of a calibration, like to show that we understand this rather than being a fundamental interest. I think it would be really neat to shake it and see like a vortex lattice and understand how like Abrikosov vortex lattices would show up in a cloud that doesn't have an edge that has continuous boundary condition as you go around. I think that would be really fantastic. Yeah, this is the hedgehog combing idea. There are these constraints on the sign of the vortices, right? Yeah, that's right. I think understanding if it would be even possible to have just one, or like what is by necessity there. Also, sometimes condensates as we make them, they come with vortices just from the violence of the evaporation. So it's sort of a Kibble-Zurek mechanism, or the vortices they're just there because of a quench in temperature that you use to create the condensate. So if there's already vortices and then we inflate a bubble, what happens to them? Well, this is where I start to get confused and look to these theory papers to tell me what to do. Yeah. I'd really like to evaporate in the shell. So rather than starting cold and evaporating, start with a hot bubble and then evaporatively cool and actually try to do the quench to being a condensate while you're in the bubble. And I think that would be simpler conceptually.
Further questions? One moment. One moment.
Adding traps, no? By modifying the traps. Yes. Another thing, this comment about rotating the bubble. If you can really rotate the bubble, you will have only vortices. But if you shake it, you will may have one vortex or 90 vortex. It will be generated in that way. Is it true?
Well, I shake, I compensate. Huge amount of force.
Just shaking along one direction,
Yeah, but if you
or
rotate it, you
yeah.
Shake it.
And that's one thing we can do with these atom chips fairly easily is modulate them at, you know, kilohertz bandwidths.
Further questions? Yeah, record, please.
Lattice of shell. Like putting a comb of a radio frequency and produce not one shell, but like a few.
Yeah, this is sort of like Chris Foote's idea at Oxford. He's done used three frequencies to make two shells. Theoretically is possible. Practically, we're limited by the total power of the radio frequency amplifier that they use. And at some point the Rabi frequency gets so weak per frequency that you're no longer adiabatic and it doesn't work. But
They don't couple so well. And the
but-
dressing goes away, right?
That's right, the dressing goes away. So in principle, we can add harmonics, but if we're starting off and the Rabi frequency isn't so high, we're in a pickle.
Anyone?
But it's a good idea.
Kind of unrelated one. Is GPT-4 already free for everyone to access? Because last time I checked, it wasn't.
What was that?
GPT-4, can we access it already?
If you pay $20, you can access it. And they only give you you can have at most 25 queries per day or something. So, you know, but I bet in 1 year, I mean, it's going to go crazy. Yeah, I think 3.5 is not so smart.
Any more? I have a question. How it happened that you contact NASA? How was this linking? You just wake up, oh, today I want to go to NASA and knock the door. How did this happen? It's not so easy to go to.
It's not, and so someone in the cold atom group at NASA is responsible for writing or constructing the experimental table that will be uploaded via radio link to the space station. I usually have a conference call with that person, and I give them pseudocode, essentially, of like making this something we've done before, but add in this radio frequency ramp, and they have internal software to convert that into the table. So it's not terribly efficient. I think I don't have the ability to edit the tables myself. In the future, I might be able to, but like right now, I have to have a conference call in the morning for maybe half an hour, and then if I'm lucky, the table gets run that day, but maybe one day later, and then the data comes to me after one more day.
So this cold atom laboratory was there before. It was already this space was already allocated for cold atoms, or you started this.
They started building it in 2014. It was launched in 2018, and the proposals came in. The call for proposals was sort of before it launched, but after it had been approved for building. Ideally, they would have had the proposals first and then built the apparatus to be ideal for us, but it was the reverse.
Quite interesting. Okay.
So I was lucky in that sense, in that all of this needed radio frequency ramps. And because it's the same technology that they use for evaporative cooling, good for me.
Just a final question. We're going for coffee, right? I know that in the presence of gravity, you can never really close the shell ideally. You always have a leak, right? Either in the poles, right? The top pole, maybe.
That's it. So if you have a quadrupole magnetic trap, this is not a quadrupole magnetic trap. It's Yaffe-Pritchard. So the bias field is always this way, and the RF is perpendicular. So there's no hole in the coupling.
There is no hole.
So it's
Because-
different than the quadrupole trap.
It's
stuff.
different from the Hélène Perrin.
Yeah.
Okay, well, that's the one I'm more familiar. My question was, can we try to do some AC type bubble configuration, like avoiding effects of gravity by having this AC field going on, and then in average, I mean, this AC averaged field.
I feel
That's in the history of the BEC.
like a time averaged adiabatic potential. Yeah.
Yeah.
Wolf Lundblad has been talking to me about that, and I don't think we've found a perfect solution yet, but he seems very confident about it.
Okay, no more questions. Let's thank speakers.
Thank you.
So we now go for coffee break.
Bose-Einstein condensates in the thin shell limit in anisotropic bubble traps. This is work mainly developed during the PG thesis of my student Elias, together with Natalia Mola, Axel Pelster. Yeah. Yeah. Okay. So here we have a small timeline of the development of BC history. What we are dealing here starts at the early 2000s, as the previous speaker already talked about, with the first experiments with atom ships and bubble traps. Then we have bubble traps with gravity compensation mechanisms, the drop tower experiments. In 2017 is when the BC goes to space in a rocket. In 2018, it goes to the International Space Station. And here we have the latest gravity compensation mechanisms. So this is, okay. So this is all to put in context what we are trying to do here. So we have I think that's the first drop tower in Germany, and more or less what's happening in the International Space Station that we saw in much more detail previously. Okay, here what we are trying to do, or what we did, was to essentially to consider the hello? So the Grosseteste situation, where we have very low depletion and weak interactions, so that we can essentially use the Grosseteste Hamiltonian. And the idea is to consider a bubble trap potential, which is a potential that essentially concentrates the particles around layer around the layer over ellipsoidal surface. So since the early 2000s, we have already bubble trap physics, some experiments considering spherical shaped traps. So the idea now is to consider what happens when we have anisotropic shells in the thin shell limit. And that's not a trivial task, because we have some papers, some works considering this thin shell limit, where we squeeze particles to a plane, or squeeze particles to a spherical shell, and the limit is usually well behaved. But when we have anisotropy, things change. So the first attempts, the first works done in the situation. For example, we have a paper with Natalia Mola, Axel Pelster, and we have the works from Salashnish. And from here, we can see already what tends to happen. Here we see that in those poles, particles start to concentrate. And the problem is that if we squeeze the shell with an infinite, a very strong infinitely strong potential, the particles will be all concentrated either on the poles, over the poles, or over the equator, depending on whether the surface is cigar-shaped or a pancake-like. Okay, in our previous works, what we did was the following. We tried to use variational ansatz for our collective wave function mainly localized over the shell. And as we can see here, we see that there is a harmonic confinement in the x0, x0 direction, which is the normal direction to the shell. And we have here another function multiplying, which depends on the tangent variables, the variables over the manifold, over the surface. And then we have to divide it by the square root of the Jacobian, of the metric. And it turns out that in order to avoid this collapse of the particles, a lot of tricks had to be used, and together with an approximation that doesn't look so nice. Okay, it's just a lot of mathematical trickery that we wanted to avoid, and to do a proper 2D limit, a proper thin shell limit. So, as happens with the other situations where we have a plane or a spherical shell, what happens is that in the thin shell limit, the tangent degrees of freedom and the normal degrees of freedom, they decouple. Because essentially we have that in the normal directions, the particles will live in this ground state of the harmonic oscillator trapping potential. And we expect to have the same thing for the ellipsoidal case, with the difference that now this trapping potential in the normal direction will change as we move over this surface. Okay, so the main idea to handle the situation is to consider a suitable system of coordinates over the ellipsoid, and for that we borrowed part of the so-called prolate spherical coordinates. So there is this system of coordinates called prolate spherical coordinates, and we took only the angular part of that system of coordinates. And with that, we can define new coordinates that look like the spherical coordinate system, and actually reduce to that system in the limit of zero eccentricity. That should be a zero here. And we have the A parameter that essentially is a quantity analogous to the sphere radius and defines the overall size of the ellipsoid. So with that, we can localize points over this surface. Okay, so in order to localize a point over the surface, we can use that coordinate system, that transformation between the variables mu and phi. Then we can localize a point P over the surface. And now what we want to do is to localize points around the surface. So we need to have now another vector, a vector q, which is perpendicular to this surface at the point P. So the idea is to calculate the tangent vectors by taking the derivatives of the P vector along the directions of the coordinates. So we have then the two tangent vectors, take the cross product, normalize it, and then we get this normal unitary vector. So with those three vectors, with this system of coordinates, we can define the so-called Gaussian normal coordinate system. Okay? Yeah. The Gaussian normal coordinate system. So the idea of the Gaussian normal coordinate system is that we have this coordinate S that is essentially perpendicular to the surface, and we have those coordinates here over the surface. So by using the normal vector, we are able then to find the transformations between this new coordinate system and the Cartesian coordinates. And then derive the metric tensor. And here we see that this metric tensor is orthogonal. It's diagonal, which means that we have orthogonal system of coordinates, which makes everything much easier to handle. Okay, and observe that again in the limit of zero eccentricity, we recover the spherical coordinate system. Okay, so what do we want to do now? We want to have potentials that we can squeeze. So we have we consider potentials that have this parameter big capital gamma. And the idea of doing thin shell limit is the limit where gamma goes to infinite. Another restriction that we have is that this small v must have the form of the ellipsoid inside of it. Okay, so the function f that defines v will be a constant over the surface of the ellipsoid, and it will have a zero derivative in the normal direction to the ellipsoid, which means that this potential has a minimum over the ellipsoid. Okay, so we proceed by expanding this potential in power series of the normal coordinate, and with that we can extract this the quadratic prefactor, which defines this harmonic oscillator frequency in the normal direction. So what we have is for each point over the surface, we have a different harmonic oscillator. We have a harmonic oscillator with a different strength. Okay, and again, we see here that in the case where we have zero eccentricity, this doesn't happen. Okay, now we can see what the problem is. If we look at this harmonic oscillator and we look at the ground state energy of each of those harmonic oscillators, we will see that this ground state energy will have this form, which depends on the angle mu, and is proportional to big gamma. So what happens is that when we take the thin shell limit, when we make gamma goes to infinite, this whole thing diverges, but worse, it diverges in the different way for different points. If we had uniform divergence, it wouldn't be any problem, because the only difference is that we would have an overall energy shift that would increase with the strength of this confining potential. But here is different. Here, for example, if we compare this energy at the equator and at the poles, we see that this difference goes to infinite, which means that as we squeeze the atoms inside this anisotropic trap, depending on the sign of the eccentricity, the atoms will collapse either to the poles or to the equator. Okay? So whenever we try to consider this limit, we must take this into account. So what can we do? Well, we must do some sort of regularization of the eccentricity. In more experimental terms, we can only consider very small eccentricities. So from the mathematical point of view, what we can do is to consider eccentricities that are proportional to this inverse power of gamma, which means that as we squeeze the potential, we must also make the eccentricity smaller. And so by considering this regularization, we observe that we can then do the limit of infinite gamma, and we have overall infinite contribution, a finite site-dependent contribution, and lower order contributions. And by doing this trick, then we are able to have well-behaved situations. To be honest, this is nothing new from people working in this field, because, for example, when we do the confinement in the plane or in this or over the sphere, we must do the same thing with the interaction strength. We must consider that interaction strength must also be controlled depending on how strong is this confinement. And essentially what I'm saying here is that in the case of an anisotropic trap, we must do the same with the eccentricity. Okay, so what does it mean from the experimental point of view? Here, for example, we have an experimental potential, experimental example. That's from the paper from Ferran, where she uses radio frequency and the usual ways of trapping atoms. And her potential is essentially this one. Okay, we have this parameter delta, which is the RF detuning, and we have the Rabi frequency that are introduced in addition to the overall trapping potential, where we get the anisotropy from. And how can we do this thin shell limit for this experimental example? For example, we can choose the omega parameter, the parameter associated with the overall trap potential, and consider this as our big lambda. So whenever we consider this well-behaved limit, if we want to consider this well-behaved limit by increasing the value of omega, we must we must do that in such a way that we only make this prefactor infinite. So we must keep this ratio finite and this ratio finite. And in addition to that, we must also keep this product finite. So if we make omega goes to infinite, we must compensate by making the eccentricity smaller. So that's the idea. That's the idea. Well, what I show here works for what I showed here in the previous slides worked for single particles. Essentially, we didn't take into account interactions. In order to take everything into account, what we actually must do is to consider the full Grosseteste Hamiltonian, write it in Gaussian normal coordinates, and then do the thin shell limit very carefully. So that's what we get when we start doing that. That's the Grosseteste Hamiltonian, the full one with the dynamics over the shell and everything in the normal direction. Where here we have this the reduced metric, which is essentially the metric over several similar ellipsoids around the original surface that we are considering. Okay. Good. So what we did in reference 7 was this limit. So we considered this gamma going to infinite limit, and what we end up with is that we have infinite contributions for the energy plus the effective Hamiltonian over the surface. And essentially what we have is the Laplace-Beltrami operator, the kinetic term. We need to have also a regularized interaction term, interaction parameter, and the end result is this cosinus potential that comes entirely due to the anisotropy of the trap. All right. Good. And here, observe that this this effective Hamiltonian is the Hamiltonian considering this wave function. This wave function defined over the surface, at the surface only. The full wave function of the system will be this harmonic oscillator ground state in the normal direction times the tangent wave function. And so that's the main idea. Now we have the anisotropic effective Hamiltonian. And the idea is to take this, everything we did here with the Grosseteste equation, with the Grosseteste Hamiltonian, could be done, for example, with the second quantized Hamiltonian, with no need for considering an actual condensate. And this opens the possibilities for us to do everything that has been done with 2D systems in general. Okay, so what we did, we first considered how good this compactification is compared with the actual 3D dynamics, and then we considered a situation with a very strong interaction parameter where the Thomas-Lamb solution is valid, and compared with numerical 3D numerical simulation, and the results seems to be pretty decent. Here we consider some experimentally doable parameters, just to show that in this thin shell limit we can actually use this 2D Hamiltonian on this 2D Hamiltonian to simplify our calculations and do and obtain predictions in a more easy way. Okay. In addition to that, we considered perturbative solutions to this ground state. So we considered the situation where we have a small power series of the eccentricities, and also we solved the Bogoliubov equations with this with eccentricities, and we did this by also doing perturbative approach, by using a perturbative approach to the Bogoliubov equations in this kind of systems. So just to summarize, that's the message that I wanted to show here. In order to actually have thin anisotropic shells, we must consider this. Okay? We must consider this here. So not only the width of the wave function will go to 0 as we do this thin shell limit, we must also choose the eccentricity so that the change, the difference in sizes between the smaller axis and the larger axis of the ellipsoid must be of the order of this normal width of the wave function. And that's what must be observed when experiments are done. And as I said, once we have this Hamiltonian, then we can do everything we did in other surface. We can consider vortex dynamics, thermodynamics, phase transitions, mixtures, and so on. Okay, that's what I had to say. I think we can.
Oh, we have time for some questions.
Thank you very much for this interesting talk. I have a question about this final part regarding the excitation spectrum and the corresponding quantum fluctuations. What would be the consequences if you wanted to do something like evaluate the quantum depletion of the condensate, the quantum depletion, and also the correction that would be the equivalent of Lee-Wang-Yang correction to this? In the continuum case, in the planar case, you have this summation of wave vectors, and then you take the integral thing, and everything is governed because you have a Healy length, right? So you have a Healy length, and then the Healy length tells you that you don't have to summate up to after this thing, so you can get the results very well. How would you do this? Because the spacing now between the modes is probably not linear, right? So you don't have a linear spacing between the ML modes. So do you have any idea so technically, how could we do the equivalent of this quantum depletion evaluation? Thank you.
Yeah, very nice question. Yeah. Well, as you said, from the more general point of view, there is not much difference in the sense that the same calculations can be repeated, with the difference now that we have this special space. Okay, So if we are to consider calculations about depletion, we must do this using harmonic, spherical harmonics, and so on. And that's just a change of basis that has to be done to do the calculations. The same thing happens, for example, when we solve the Bogoliubov equations. That's the same thing. In order to solve that, if we have, for example, the spherical case, we can do everything exactly, essentially. The calculation is essentially the same as the one in the plane, with the difference that we must use different bases. Oh, I'm not sure of that. Oh, yeah, I think so. I think that there's not much difference from this point of view between the symmetric case and the non-symmetric case. Yeah, everything should work more or less the same way. The only thing that we have to watch out is that we cannot have an arbitrary anisotropy. But everything, I'm pretty sure that there's no reason. That's because there's no mathematical reason to be different. There's no extra divergences, no extra poles, no extra mathematical things that makes the series not converge. So I think that is should work.
I had one question. Would it be possible to figure out what so mean field repulsion by adding more atoms into the cloud should overcome this, right? Like you should be able to make it squeeze out. Would it be possible to figure out, how to make them touch as a function of eccentricity, for example, by adding numbers?
By adding numbers, which means adding the effective interaction, so to say, right?
That's right.
Yes. Yeah, that's possible. That's possible to overcome that. But then we do overcome that, but then we do not have a Gross-Pitayevsky dynamic anymore. We don't have the same structure, the same simple structure that we have here. What we have is we will have a very strong background. We must have the situation where we have this very strong background and oscillations over that. So that's a kind of restrained situation, but that's true. That's true. Another way to overcome that collapse would be just to make interaction stronger. Which would lead to a different thin shell limit here, totally different.
Excuse me. When you made the evaluation of the energy, the potential, could you see some critical value for epsilon to reach in this thin shell?
Yeah, there's not actually a critical value exactly. It's there's no fixed value. We must have the situation, the experimentally analogous situation to this mathematical statement. That's what we must have. So the idea is that we want to have this epsilon bar finite while our gamma goes to infinite. And from the experimental point of view, when we make gamma go to infinite, what we do, we squeeze the trap. We make the width of the wave function smaller. And by comparing this width with the eccentricity, with the size of the larger axis and smaller axis of the ellipsoid, we see that a good criterion to keep that situation is to keep this difference between the axes at the same order of the width of the radial wave function. So if we squeeze too tight, we cannot have this difference between the two axes too large.
And I ask you just a quick last question. Is that did you how is the density of particles? Does the density of particles can affect in some way the bubbles? And is it dense? Is it diluted? How is it?
Yes, as Lundblad said, another way, if we use more particles, we, for example, could have a mechanism for stabilizing this collapse instead of doing the limit in the way I described here. So another possibility for stabilizing the system would be with this strongly interacting situation. And then there is all possibilities in between, what happens in between, that also can be analyzed.
Did you make a plot regarding this epsilon as compared to the ratio of the density in this axis to the density of the poles? So as we have a feeling of, okay, I can go through this and see the difference when it will be more clear. Did you have a plot like this?
I don't have it prepared here. I can show you the paper.
Okay.
And
Okay.
yeah,
Okay.
I don't have here prepared.
Okay. Thanks a lot.
Oh, we're recording. No, serious stuff. Oh, Denilson, it's a very nice calculation. I know that this has been going for many times. I want to ask a question about perspectives. Okay, we solving the problem of the bubble in different ways with different parameters. And then you said that perspectives, we're going to study thermodynamics and some other things. What do you have in mind? Because, for instance, formation of a condensate in a bubble may be very interesting, but nobody speak about, right? I mean, evaporation and everything. We try to start with something and fill it up the bubble. So what do you have in mind for thermodynamics? And why is this a nice system to study thermodynamics?
Well, you have a nice paper on thermodynamics yeah. Actually, no, there's also Monica Caracanhas has a paper on bubbles thermodynamics. I think it was the symmetric case. All right. For example, the same thing could be done for the non-symmetric case for this ellipsoidal situation. That's
but you know, the most
that's the simplest thermodynamic situation. No phase transition. That's something that can be readily done.
Oh, okay. The most interesting things in bubbles is what?
Well,
is the curved space?
Well,
if so, what we are looking when we go for the thermodynamics in a system like this, that nobody has thought, or maybe has a lot of interesting things to be found.
Yeah.
This
so,
is.
I think the same question was made to Nathan, and he
Oh no, it can be for the first speaker as well.
And from his point of view, there is the experiment in itself and all the possibilities that are open from that. I am a theoretician, mostly from so for a few theoretical formation. So what's interesting for me is the curved space. And the possibility, what happens when we put vortices on that? We have the topological constraints, right? What happens to the dynamics of those vortices when we have anisotropy? Maybe they get locked in the poles. Maybe their dynamics are restricted to the equator, depending on the value of the eccentricity. all those possibilities are open. From the point of view of the dynamics of vortices, then there is the phase transitions on the system, finite size effects on the system. For example, we can take the system, do thermodynamics. We can use grand canonical ensemble, compare what happens with this finite situation. Yeah, it is exciting. Yeah, I'm happy with those possibilities. If I can carry on with any of those possibilities, I will be happy. Yeah. Yeah. All right. Yes.
I think the curvature of the background spaces, so one thing
Yeah.
so
You know,
beyond the vortices, I think one of the things the Illinois group has seen is that as you inflate the bubble, you see, trying to understand the dynamics of how the inflation actually works could be interesting. So if you start off with a condensate, actually drive it normal to the inflation process, and then it becomes a condensate again. So you get, what some of the condensed matter theory people, they call it a re-entrant phase transition, and that it doesn't mean much to me, but they get excited about that. Where you see as you're varying a geometric parameter, you're driving phase-space density differences, and that's kind of strange, and that seemed to be fascinating. That's right. That's right.
yeah. Yes.
I think the field is transitioning a little away from, where we see something that is curious and interesting just because we can, and then you're sort of transitioning as it becomes more interesting. You need to justify it by looking for a longer view, a decadal type view.
Yeah. And of course, what's doable from the experimental point of view is always fuel what we are looking for. If we see that, okay, they are close to do that, then we, as theoreticians, we run after what you should expect to see in the experiment.
I have just a small provocative add on this discussion. One of the biggest problems on gravitational physics, for example, is really this interaction between gravitational waves, for example, and dark matter, right?
Mm-hmm.
So as you probably know, Bose-Einstein condensates are nice candidates for dark matter. For the moment, probably one of those shells are static, but we can probably think of ripples on top of those produced in the lab. And this could mimic somehow gravitational waves. So if we could do a map between this and in terms of field theory, right? And gravitational problem could be very nice. For example, it could motivate investigation of quantum simulations, let's say, or emulations at least, of these gravitational problems. And this would be amazing. I suspect that we could excite a lot produce lots of attention within the communities of gravitation or astrophysics and gravitation, for example.
Yes. Yes. Sure.
Any more thoughts? All right. Well, I think it's time for lunch then.
I just want to tell you that you received places for in your folder, you receive places to have lunch here close. There are 4 places and you can choose between